Okay, let's get started. Okay, let's get started. So today we'll talk about large language model, and we will explain or explore a little bit why it has been spread every corner of the world right now, like kind of reshaping our society, our daily life. So basically, we'll talk about how this can be used for our general social good. So before we start, this is our line, and we'll begin some of the backgrounds, and then we will try to focus on two topics, and I will explain a little bit about the training project my group are doing right now. So first of all, backgrounds. Since we talk about AI, and this is kind of a history that right after World War II, there's so many efforts that they want to transform some of the military advancement to the civilian kind of application. And those founding fathers start to have this concept of AI. And in, long story short is that we want to create a machine that equipped with a human-like intelligence and replace some of the, redundant kind of, manpowers to resolve some of the daily tasks. But like I said, it's kind of a long history. But not until I would say around 2000-ish. So many theory have been developed throughout those decades, but up until like around 2000, there's a booming phase, what I call, where we have this a little bit newer concept, which is called deep learning. And one of the booming, driving force behind this booming phase is that we have many newer chips, for instance, like a GPUs, to enable the scientific computing. We do all the matrix operation, and they can be used for parallel computing and all that. So this was one of the driving force behind this deep learning eras, and we also have a widely public available data set, and I provide a couple of you here. One of the famous one, ImageNet right now, especially for vision, all the pre-trained model have been using this data set, and I think some of you may be familiar with the CIFA 10, CIFA 100, that we still report the score for classification, which is probably the pre-training phase where people use to examine their performance. And there's a lot of effort for architecture as well. Famous one like CNN, RN, where CNN primarily used for vision, while RN primarily used for language. And later, I think it's around 7 or 8 years ago, we were introduced a transformer, and this is where kind of a bridge the gap between those two intelligent domain, kind of combine, fill the gap between vision and language. And right now, we start to have this uniform architectures to address those multimodal tasks, including both language and vision and many other multimodal kind of tasks and beyond. So right now, we kind of living in a new era, right? So we have generative AI, and examinatory techniques such as ChatGPT or Sora. So GPT is mainly focused on language, and Sora we generate like videos, lifelike videos, and all that. And one of the driving kind of technique behind this is larger model. And of course, people talk about diffusion model as well, but today we're going to focus on larger model. And this has been getting a huge attention, both in academia, but also a industry as well. So you can find, for instance, if you have friends working for the industry, they were talking about how their research people are developing newer large language model, and how they kind of compete each other, and outperform some of the older method on the benchmark. So this is our focus. We'll talk about larger model, and it has been creating some direct social impact. And have been used for many social sectors. Like for instance, like energy sectors. This is one of the work I wanted to introduce, like a Fusion LLM. It's created by my group, and we are the scientists right now at the National Laser Lab and Los Alamos. People are using our technique algorithm to guide their empirical design. Manufacturing, some of the fulfillment center for Amazon, they're using large language model-based solution to facilitate the kind of human-machine interactions and helping them to kind of improve their productivities as well. Healthcare, of course, people may heard Pronama compared to prior method for the proteins with the instructions. Pronama has pushed the limit and they gain even better performance in compared to prior arts. So many others, but I don't want to go through each of them. But you can see how large models have been reshaping our life, and right now living in every quarter of our daily life. So due to the time limit, we will probably focus on energy and robotics, probably because we have some sponsored research in those two domains. For energy, we get some grant from the Department of Energy, design some of the technique for instance, nuclear fusion. I will elaborate that in the slide. So let's dive into the first topic, which is large model for energy. And probably we'll focus on two topics. The first one is sustainability, which is quite important. Then we talk about how we can use large model for the AI innovation to advance our energy solutions. And specifically for the sustainability, the first research question we want to ask is that how you can achieve energy sustainability in the era of large model, because we are developing large scale models, and by giving the current energy productions, can we remain sustainable for the development? So let's talk about the challenge first. So right now we know the model is super powerful, and it has kind of reached the human level intelligent for many tasks, like writing an essay or ask questions and all that. And apparently the model right now we're building on using the kind of philosophy called the scaling law. And this basically, people focus on over parameterize the model and also use increasingly large scale data set. And the two plot here showing basically with the increase of data set size, we have the model performance. You can see the training loss decrease. And also if you parameterize your models, the performance also increase. So the y-axis is the loss. Well, this is obviously functional, and this creates some kind of air quote miracles in the current AI domain, but also facing the challenge. The challenge is that we demand a lot of energy to train our models here. And I quote here, and I think it's one of the new from New York Times, that if we continue doing this, if we continue using the scaling law, the power consumption by 2027 will equal to some of the middle-sized nations like Argentina, down to Sweden. So we definitely want to think about alternative. How can we, on one hand, we want to create more powerful AI solutions, but also on the other hand, that how can we make it sustainable of such a development? So before we dive into some of the solutions, let's look at the model we're dealing with from the architecture side. So we talk about architecture first, and we dive into the training. So in general, right now, all the large model are built on top of the architecture for the transformer. We kind of stack layers of transformers block, where in general where the deep learning comes from, because we stacking a lot of layer of transformer together. And within, if you zoom in to look at the transformer, one of the key component for the transformer architecture is the self-tension layer here. Since we're dealing with multiple head, we call this multi-head self-tension, where basically we have the query, we have the key and value. So first, the query and key multiplied together, we have the attention scores, where the attention matrix multiply back to the original values, and where the sub-attention mechanism were working in such a pipeline. So this is architecture, very high level. There's a lot of variations, but I think this is good for now to understand that how important understanding transformer and understanding the core component of transformer sub-attention will be very helpful for our algorithm design. And then let's talk a little bit about the training. So right now, all the larger models are using like being trained and being developed using two phases of training. The first phase is called the pre-training, where we have a lot of data and train on the models. And we have this foundational model where the foundational model has been used. Oh, by the way, so this phase, the first phase is primarily dominated by those major companies. So we don't, in general, I think at the university level, people care about the pre-training. That's because, we play with those publicly released model, pre-trained model like Llama or mini GPT and all that. But these are dominated by those major company because they have access to those large scale data and also have extensive GPU resources. So this is a pre-training phase, which is basically contributed by those major company. And once those company perform pre-training, they release a model weight. For instance, using Llama as the example, then for the end users, we perform fine tuning on the algorithm on the target data set where we can accommodate various downstream tasks. For instance, you want to train a large language model for translation or do the calculation, solve the math problem. You want to use language model for low control and all that. So this is general pipeline for training. We call this pre-training and fine-tuning. You can see majority of the contribution what we can participate is in the second phase, which is fine-tuning phase. But one of the problem we already understand that the over-parameterized model, training them from scratch, not from scratch, fine-tuning them from scratch is very expensive. Like if we tune your model of the pre-training model, it's just literally impossible. And because of that, in academia right now, people propose a solution called the parameter efficient fine-tuning, where there's seeking the efficient adaptation of those pre-trained model. And obviously, a couple of few things we need to be mindful, which is that we want to decrease the computation and the storage cost. And also, in terms of performance, we want to have the model has equivalent performance in the full fine-tuning. And right now, there's a couple of few solutions on the market. So first one is partial tuning. So we were talking about we have all the transformer layers stacking together. Instead of tuning all of them, each of the layers, we only have to tune for instance, a couple of few layers, maybe the last layers are good enough to kind of transfer the knowledge from the source domain to the target domain. And a second kind of solution is called actual modules. And it's more famous, to be known something like a LoRa. We are at a little bit extra module in the middle. And instead of tuning the entire transformer graph, we only have to tune the actual module, maybe like a LoRa-like module in the middle. But our group primarily focuses on the third solution, which is called prompt tuning. The reason why we focus is that it actually has the best kind of a trade-off between the parameter overhead and the performance. And you can see it's just very straightforward compared with the previous three. We only have to add a little bit like a parameter token for each of the input at each of the input layers, rather than adding parameters in the middle or to tune the entire layers. So one of the advantages, like I said, is that it's just parameter efficient compared to other two, and also can have equivalent performance. So we will focus on that. We actually developed a line of work built on top of the prompt tuning, and primarily we want to address two questions. The first thing is that if you look at the general framework, you can see they only care about the input of each layers and then add the parameter tokens at the beginning of the token sequence. But we also talk about how transformer works and what's a core component of transformer, which is the central attention. So what we want to focus is that can we also consider the core architecture of transformer? Adding a little bit, actual parameters within the central attention. Well, this is naturally, very intuitive, but naturally thinking that we can improve the performance. Another thing is that they either focus on the vision side or the language side. Nobody tuned the multimodal model simultaneously, but in reality, majority of the downstream model, people care more about multimodal models. They don't, they, for real world kind of applications, pure model only can be used in, either like a language side or vision side. Can we combine it together? So these are two endeavors for our group, which is consider the architecture, but also tune the multimodal model simultaneously. And this is a very general pipeline. If you look at the very left figure here, you can see there's some similarities, right? So we still adding some prompt, parameter prompt at the beginning of the token sequence. Here's a math expressions. So this is nothing new beyond the prompt tuning, but we also have a little bit of fire here in each of the transformer block. So the slow fake means that the block is frozen during the tuning phase. And we're adding a little bit of fire because if you look at in the middle, this is where we're adding a little bit of parameters for the 2kV. And specifically, we're adding a little bit parameters in the query and key. We adding some parameter in the value as well, but later, empirically speaking, that doesn't necessarily helping for the performance. So we only end up adding the parameter in the query and key here. Once we add in the newer key and the value, the remaining kind of operation stay the same. So this is where we calculate the segmentation score, and then we feed into the FF layers. So this is how straightforward. We didn't change much. We're still following the prompt tuning paradigm, but we're looking at more micro level, adding some parameter for the query and key. And later I will show you guys how this can be beneficial for the result. So so beyond that, we also focus on the multimodal models, and this is one of the examples. So this is one of the multimodal model that people are using nowadays. So we have this larger model at the backbone here, but also have a vision encoder, and this is where we can encode and process both the multimodal tasks, which is like giving an image, we asking some question about regarding the image. And the general pipeline is that the image is encoded by the vision encoder, and then combine the embedding with the question as well, where we can have the output. So during the tuning phase, we follow the same paradigm that just adding a little bit parameter prompt at the beginning of the sequence. And here is the same. We're adding a little bit parameter prompt for the larger model and concat the features from the vision patch as well. And by doing this, we can simultaneously train the multimodal model of the both the vision encoder, but also the larger model background here.
Could I have questions?
Yeah, sure.
Yeah, so for that block, the vision encoder block, what kind of a prompt, additional prompt, the paid prompt that you are adding to as an input?
It's just
are they tokens or
they are tokens, and the token size is the same for the image patch. But they're like randomly initialized, and we use a gradient descent to update the prompt here.
So they are random tokens, but do you actually fine tune to actually train on the what the token will become eventually?
Right. So think about this. In general, when you talk to larger model, is that you give the larger model hard prompt. When I say hard prompt, they say, for instance, what's the weather like today? Or no, that's a bad question. They say, what's the capital of Hawaii? So that's a hard prompt. That's a human language. But here, the prompt we're adding here is called a soft prompt, where human cannot read it, but for machine have a better understanding what content will be. Because essentially later we explain what's the mechanism behind this soft prompt. Because for the hard prompt, the larger model is searching in his brain what's the best answer for that? Well, for the soft prompt, it's kind of the same mechanism, is that to activate the neural pathway for the model so they can better accommodate the given task. So that's sort of the same mechanism, but the very high level, it looks different. It's called what I call the soft prompt and hard prompt. And then, even for the hard prompt, nowadays people are publishing books teaching people, users, how to better develop your prompt so the model will serve you better. But that's not gradient based, right? It's more like an experience based. And it's more like a model by model case. But using this, we use a gradient search to optimize the better system.
But at the end of the day, those two additional
will be frozen when we perform inference.
Gotcha.
Yeah.
But there's no additional information provided.
No, there's no additional information.
Gotcha. Okay.
So there's some result. So we talk about, at the beginning we talk about like partial tuning, we talk about adapters. VPT is another prompt tuning, it's called visual prompt tuning. You can see compared to those prior arts, our training parameter is much, much less. And this accommodate our promise earlier that we define much less parameter, and we also gain the performance speed, runtime performance, and compare the performance, the actual performance, also can see the improvement over these baseline here. But one thing I want to point out, which is quite informative observation, that for our design for some other tasks, and later we talk about how the energy advancement, is that if you look at the model, it's actually have been pre-trained on this, the data set with this scale. Well, all the target domain benchmark, you can see the target data is much, much smaller. So what this is essentially telling us is that it's actually have very powerful knowledge transfer ability from the source domain to the target domain. And as I said, this observation helping us to design some other solution for different downstream tasks. And later I'll elaborate on that. Okay, so this is kind of addressing our first concern about the sustainability. We take it one step further, and there's long way to go, of course. But let's focus on the second topic, which is advancements. And for the advancement, the key question is that language model is very powerful, reshaping our daily life. Especially for me as a language learner, I use large language model to polish my essay, polish my proposal all the time, and even asking the large model to help me walk through some of the papers. But can we also use the large model power to reshaping the paradigm of energy innovation? And this is a very interesting topic, and I want to share a very interesting encounter. So I was invited to give a talk at the University of Rochester, and they have a big laser lab. It's a national lab where they use all kind of a laser technique to examine the ICF process. So ICF is short for basically the nuclear fusions, but it controls nuclear fusions. The process is like that. So we have this target, and we have a laser to hit the target, where the target will start to compress by the energy, and then there's explosions where we can have the energy, use the energy for the energy protections. But the question is, if the laser is too strong, we're not creating a controllable energy here. We're creating the nuclear bomb. So how we can ensure that the laser hitting a target and creates compressions, or on the other hand, that we're hitting the target too hard, we create a nuclear bomb. So there's a kind of middle ground we want to examine, and they do have some preliminary result. You can see here, this is actually the true distribution or the true plot for this process, where with intensity of the laser, how much energy emission will receive. And for another plot here is the model they built. You can see there's a huge gap in terms of the prediction. here, which is problematic. Somehow they cannot directly use their model they build to guide their design. So the challenges they're facing is that the data is limited, and the model, of course, is performing kind of on par to the ground truth. So those sort of problem they kind of want the AI expert to help them to address. And then one thing to another, we've been talking and we have been forming the collaboration for almost like 1 year and a half. And I propose we can use larger model to solve this problem. And the first question, not first question, but a couple of few questions I want to convince my collaborators is that why larger model? The first question they all ask is that we don't have limited data. They have like 100 shot annually. So you can see it's not 20. And especially in the deep learning era, you are training the model, which is data dependent. And it's very hungry for more data. Otherwise, we kind of the underfit cannot find the best kind of mapping between the input and output. But what I propose a larger model because it has been pre-trained on the vast data set, and there's a lot of knowledge they have been learned for like physics, and such a general knowledge can be transferred from the broad general domain to the specific domain of fusions. And specifically, we also talk about prompt tuning. And here I kind of visualize that those soft prompt can be used to generate not necessarily generate, but activate the neural pathway within the larger model. And this is quite important because they want to basically tell the model, what kind of knowledge we need to use to solve this problem. And next question we want to ask is that, this is, we talk about laser, how the laser will hit the target. And obviously this is kind of time dependent. So it's kind of time theory task. And why larger model can be used to solve the time theory task? Naturally, larger model can be called like an autoregressive behavior. And you can see here is that they always keep predicting next token by considering the input from the previous, historical information. So such a autoregressive nature is very helpful. And this is natural feed that can capture this ICF time series patterns. And finally, there's little emission here. But finally, one of the critical problem for this ICF process is that for many classic physics explorations, we always try to find the first principle rule to guide the model design. But however, as we explained earlier, that this ICF process is highly nonlinear. We don't have enough data to understand the true distribution looks like. So there's no first principle rule to guide our model design, which is problematic. But one of the benefits larger model can bring into this project is that larger model has this vast parameter space. So with the proper prompt, we can consider this process is that we're looking for the function, mapping the input to the output. So we essentially perform the function approximation. So by having those three individual, kind of asset together, I kind of convinced my collaborators, okay, there's some potential that we can use larger model to solve this problem. And here is our general framework design. So we have prompt. This is basically telling our model what kind of task we're dealing with, and we have this pre-trained llama. And also have this another module which is encode the input data here. So for the first proportion, the fusion specific prompt, we have a couple of few things. What kind of task we're dealing with. For the task, how long of the sequence, how long is the input, and also for our input, we kind of have more fine-grained information regarding like what's the minimum value for the laser intensity, what's the maximum value, how long of each step. So telling the model all that is, we find very beneficial. It's more like you are the boss telling your employee, what kind of task we're dealing with and what kind of the constraint we are facing here. And for the signal digestion channels, it's kind of straightforward. So this is laser intensity, and you can see this is time. It's purely time dependent. What we're having here for the data is that we have like a 400 steps. you can see the laser start to increase the intensity where we reach the peak, and then it's cooling down gradually here. And this is associated with our energy emission. When we hit the target, the target starts to compress. We start to have the energy emission, then cool down with laser cool downs. But another interesting design we have here is called a confidence scanner. For the domain expert, they care less about how you design your method, as long as you can have a very decent prediction on the data we have. So we have 100 shot. We use 80 shot for the training, 10 shot for the validation. We have 10 shot for the testing. And later we'll show you guys that the prediction is pretty decent. But the one question they also want to ask is that how much we can trust the model. And long story short is that we use the token entropy as kind of an indicator to understand how much we can trust for each of the prediction. Because if you have a token with a high entropy, meaning for that specific step, we are the model is less confident about the prediction. If we have lower entropy, then the prediction from the model's perspective, is supposed to be have a more confident predictions.
Question. So for the fusion specific prompts, do you actually give them give the LLM the equations as well?
We don't have equations. We don't have equations. We telling the model, what's the task? Some of the detail for the inputs, high value, low value. We have 400 step, all that. It's more like a factual descriptions, but we don't have models for the equations for the model to understand.
But if I give it equations like like general physics or any related physics equation,
I see what
is
you
it
mean.
going to be helpful?
We honestly didn't try that, but I think that's a very good suggestion that maybe we should consider incorporate that equation. One downside for potentially including the equation, like I said, because we don't have first person rules out there. I don't know if some of the related equation would be helpful, but I guess should be. But at that time we didn't use any equation because of that. We thinking there's no guiding philosophy behind this, and we somehow don't want to step out of the way rather than a model to do the math for us.
But overall, the goal is that given the laser intensity, we will try to estimate the hot electron energy.
Right.
Okay.
And also associate with the confidence score. And then I will show you guys some empirical result figures. So here's some empirical result. The first thing we try is called long chain result. This is very popular nowadays for large model. They perform like a few-shot learning, but here I use few-shot learning is a little bit different from the conventional deep learning kind of terminology for few-shot, because in general for the deep neural net, when you say few-shot, there's a gradient involved, right? We have to use backpropagate to kind of update the parameters on the given samples. But for our, within the concept of deep learning, we kind of feeding the sample to the model, but there's no gradient involved, so we are not updating any parameters. So here we basically just showing two shot both input and output for the model, and then the model to directly perform inference. So you can see it start to catch up the pattern for the hot electron activities here. So because you can see you start to have the peak and drop down. And obviously this is a big performance gap. You can see this is not aligned with the ground truth very well. But by giving one more shot, it starts to recover from the arrow here. So you can see that the peak is kind of simultaneously having the gap between two shot and three shot. You can see the gap becomes smaller. And then for training result, we choose a few comparative methods. So TimeLM is released last year. It's one of the very famous model for time series forecasting, and we're naturally thinking, oh, it's dealing with time forecasting, and this is a time forecasting problem. Can we use this to, as a strong baseline? And somehow we can see it actually can capture some of the patterns, but it has this weird second peak. And you can see this is why our unique design is better. You can see the prediction align much better than the time. And also we compare with transformer-based solution, also LSTM. LSTM is one of the RNN-based model, very classic model. So you compare with the concurrent method, but also some of the classic deep learning model for transformer-based and also temporal-based models. There's obvious advantage of the design in compare with the previous methods. And here's another thing I want to share with you guys. Like I said, we use the token entropy as an indicator, and basically, we have a high entropy, meaning the prediction is not reliable. We have a low entropy, means the prediction is kind of strong. And one of the hypotheses is that if you have a strong prediction, then the error you make is supposed to be smaller. Well, you have a high entropy, meaning you are not confident about the prediction, and the error is supposed to be high. And you can see here, the bluish line is prediction error. It's bouncing up while the prediction dropped, right? And in general, when we have this flat, I would say flat, not that flat, but it's relatively low regions, the prediction is relatively high. Okay, so some of the takeaway, for larger model, we can transfer the general purpose knowledge to the task specific domain, and we can use prompt tuning to facilitate the tuning pipeline, so we don't have to consume a lot of power like pre-training phase. So this is one of the advantage. And larger model by natural, it's autoregressive model. So they can be used for many time series forecasting. We're showing the example of our model, but also the time series LM. This is our two kind of example or demonstration that it can be used for many time series forecasting tasks. One exciting thing for the larger model, for the second example we're showing you guys, is that it actually has the potential to become a the powerful tool to address many AI for science problem. And right now, many funding agencies are pretty slowed down the AI for science, and people are debating what kind of AI tool we can make to facilitate the science explorations. And so this is one of the small steps we're moving forward. Okay, so
sorry, I have a question. So can you go back to the network architecture?
Okay.
Yes, yeah. So I wonder, do you guys have any application study to see how important the fusion-specific prompts are?
Oh, yes. We did all the application study for each of the categories. I cannot tell you off the top of my head which one is more important, but we definitely perform application study for each of the module here.
I see. Do you actually, so that actually matters, or?
It matters a lot. It matters a lot. One of the drastic situations is that we remove all the prompt, and the model performance decreased a lot. So that's the thing I can tell you. But yeah, we have the paper online. If you guys are interested, you can sure check it out. It's quite interesting kind of project. So this is a takeaway for the energy topic, and I will continue to talk about robotics, which is also quite interesting. And for robotics, the two things we want to focus on. One thing is behavior. Another thing is interaction. For behavior, the question we want to ask is that can we make the robot achieve human-like versatiles? And there's a saying that for AI or versus human, hard is easy and easy is hard. And to translate this is that, for instance, hard is easy if we're showing people a photo, and for instance, a photo of a group image, and asking how many people are in the photos. And for us, we have to count individual person, right? But for AI, this can be processed very fast in millisecond scales. Well, if we flip the coin for human, we can wash dishes on every day, right? It's relatively easy. It only take a few seconds to finish washing one dish. But for AI, it's pretty hard to make the AI-enabled robot to clean up the dish and put the dish in the shelf. So this is what I'm saying here. How can we make the robot more versatile? So here's some preliminary knowledge. We use reinforcement learning, imitation learning, and also evolutionary learning to teach the robot behave like our humans. But somehow this is super challenging because in general we need a lot of data to train a model. I know one of the key challenges is that the optimal state action space is huge, is just so huge. And searching such a combination of the action and optimal status is also very hard. So to kind of translate what I say here is that people start to toss the idea of the role model. Long story short is that we want to make our robot having this understanding kind of internal representation of the environment, and without such a internal representation of the environment, it's pretty hard for a model to understand and to plan and to act by giving a certain circumstance. So how to build a role model is one of the challenging tasks for us. And as I said, those previous methods is not very efficient because the searching space is too big. And by giving such a challenge, starting from last year, people having try to use larger model to address this, and they can incorporate the vision kind of encoder into the larger model. What do we call it? Is multimodal large model, or some people call it large scale vision language model. But it's essentially the same. We have a vision component, we have a language component, and we can train the model end to end. It can directly generate the actions. And one of the benefits, actually a couple few benefits for such an approach is that, first of all, the model has been pre-trained on the vast data. And for both vision and language, we can form a kind of unified representation space. And this is very easy for the robot to generalize from thing to thing, because all the knowledge has been learned from the vast scale data during the pre-training phase. Another thing is that those robots can interact with our humans and always receive feedback from a few humans, and because of the feedback we receive, it kind of correct their behaviors, and it's very easy to adapt. And on top of that, the massive pre-training and in-context reasoning, because of this adaptation, working with different tasks, working with the humans, it's just easier, much easier. Let me put it this way, much easier to build a role model for robot. And for our group, we actually observe a kind of a simple but also intuitive, things regarding the task we are facing, the robot facing on a daily basis, which is that different tasks may have different state distributions. And give you one example, for instance, like a domestic, like household robot and industry robot, they may kind of share some similarity in the task space, right? In compare with autonomous driving, obviously the task is so different. So what we're looking for from the model side is that so first of all, the large model has a vast parameter space, and what we're looking for is that how can we accommodate various tasks. So essentially, we can capture those valuable manifold for individual tasks. So we can generalize the model to accommodate variant application, but also remain task-specific perceptions. So within the having this observations, we design a method called the MOE prompt. So MOE is short for Visual Expert Prompt Tuning for our larger model-based models. Long story short is that we creating this gating mechanism, and this gating mechanism will taking the input taking the input and dynamically select individual prompt to determine which prompt should be used for the specific task. And because of this, dynamic prompt input, we can make the model, generate a proper neural pathway to figure out what kind of a neural pathway for the given task we should use. And this is really provide our model more flexibility to various tasks without, touching the larger model parameters, but only have to focus on, the input prompt using this what we call it MOE. So individual prompt they choose will guard specific task here, and this is naturally will accommodate various tasks. And I give you guys a few examples. We don't have fancy equipment, so we only have one real world kind of result here, but you can see by testing in the various simulation environments, and this is a household robot. This is indoor navigation, picking up things, and this is autonomous driving in the Tara simulation. We do have one robot. This is a wheel roll kind of operation. So this is one of the wheel roll robot arms to pick up stuff by giving the command by humans. And this is showing some promising result that at least in the simulation role that we can use as MOE prompt design to accommodate various. Okay, so next question is interactions, and this is kind of natural because if you want to deploy the smart robot in a society, one of the questions we want to address is how can we promote the trustworthiness and how we can promote the acceptance of the robot. And this is purely dependent on the very healthy human-machine interactions that the human can better understand the robot behavior. I don't want to use specific healthcare as an example. So for instance, if you feel sick and you go to the hospital and you have to, having a lot of test results and you have to see a lot of people's different specialists. And one funny thing is that if you talk to different medical practitioners, they may give you different answers by having the same if you have kind of the same issue, but by talking to different people may give you different result. And this is sometimes very frustrating and confusing. So we were thinking, like, can we use large model to solve this? And we can use large model as a smart agent. Very high level is that whatever large model we use, we can use the large model as an agent to retrieve some of the AI tool, and then use the AI tool to perform analysis of the medical exams you have. So instead of like talking to different people, we can use the kind of uniformed platform to solve the problem for you, and provide more context-aware analysis. Another thing we want to highlight using large model is that we all know large model has this COT kind of behaviors. By decompose a very complex problem step by step, each of the steps can be considered as a kind of symbolism, and it's very easy for us to examine if the intermediate output or result are reasonable. And we can definitely reformulate this as a neural symbolism because we do have a neural network, and also the result is human readable, which is a symbol. So combining those two things together, using large model as an agent, we only use that platform, and the platform will call different API, different AI tool to solve our problem, but also each of the intermediate result can be understandable and evaluated by our users. And building on top of this, by looking at the previous slides and this slide, so instead of like talking to different medical practitioners, we can use a larger model as an agent. So all we have to do is feed individual records into the model, and they will perform analysis. And each of the intermediate result is evaluated by our models. They can see step by step how they can reach the final agreement. And this is kind of one of the popular design in the medical AI domain. that you can incorporate large language model as a assistant to the medical diagnosis. Okay, so takeaway, we can make robot more smart, and larger model obviously can equip our model this in-context reasoning capacity. And in the middle grounds, for each of the step, we can perform step-by-step evaluation and incorporate that neural symbolism into the model, so we can increase the trust between human and robot interactions. And finally, what we see here is that large model can really liberate some of the specialized service and make them more affordable and accessible. Let's say that, and this can obviously in turn improve the social good. So what next? So we talk about efficient fine tuning. So we only focus on the second phase of the large language model development, and because the first phase they require large scale data and also require extensive GPU resources, but one of the solution we propose is that can we make the model smaller? So if we make the model smaller, we can pre-train the model, and also can we selectively choose some data for training? We can find some of the prototype knowledge that can easily generalize in the general or represent the general distribution for that specific task. So we don't have to use large scale data to train, but some prototype data or prototype knowledge to train our model. So this is one of the efforts that we want to pursue. Specialized model, specialized robot. Robot can pick up items and do the navigation, find some of the items within the house. So that's what we call specialized robot. Or can we evolve to more generalistic robot that can be more helpful to complete more general tasks for humans? So these are another kind of endeavor we want to pursue for future work. Okay, so thank you guys. This is pretty much for my talk today. Do you guys have any questions?
I have a question regarding the first line example.
Okay.
The one, do you mind go back to the slides? So I wonder for this case, are you more performing imitation learning, or is it something different? Like this is, so you basically have a simulated manipulation, right? And then you want to transfer the knowledge to real world manipulation. So is it like a imitation learning case where you?
No, so the reason we probably test our algorithm in the simulation because we don't have hardware. So that's the reason. It's not because we don't want to test in the real world. Those robots are very, very expensive. The robot arm we borrow from the group in Texas. But that's the best we can do so far for the physical world testing because of the lacking of the equipment, and that's pretty much it. But here, what I want to show you guys is that for various tasks, we don't touch anything for the backbone model, but only using this so-called gating, mixture of expert prompt tuning. They can actually do many tasks without changing the main body of the models here, which is quite interesting. You can consider the main body of the model as a brain. All we have to do is stimulate the right position of the cortex, and it can do the proper thing. And one of our ongoing project is called kind of neural embedding editing. Is that to examine adding a little bit like actual module in the middle, like examining some of the embedding, how the embedding change will telling the model what's orange versus a cat, and what's going up and down by editing some of the embedding in the middles, and kind of unbox the black box nature of the model.
So I guess for back to that example, right? So here for that robotic manipulation task, what kind of prompt tuning did you perform for that specific case?
Can you say it again?
So if you go to the next slide where you show the robot actually grasping stuff, right?
Okay.
So what kind of a prompt did you provide to that case? In order, so I suppose.
Oh, you follow the robot still when you perform inference, you will give the robot
Some prompt, right?
no, you give the robot the verbal kind of instructions.
Right.
Like for instance, open the drawer.
Uh-huh.
So you still have to talk to robot
Okay.
to let the robot follow your instruction.
I
So
see.
here we don't use soft prompt. So soft prompt is so soft prompt is only by looking at your instructions, say open the drawer, but you still have to give the robot some instructions. Otherwise,
So you have a text instruction, and then that text instruction will change the.
exactly, that will change. That will change the. Oops, let me go back.
Okay.
So that would naturally change here. It would naturally change the prompt selection here.
Gotcha.
So
I see. So this thing actually kind of filters through your actual text prompt.
exactly,
Okay.
exactly. So we have the gating to kind of a dynamic snack which prompt we should use by giving certain sequences.
So I guess what I'm interested in is like what's the with and without this module. For example, for the video that you showed there, it's probably already with this. You have an example of with and without this additional prompt tuning.
I do not have I didn't prepare the videos, but yeah, that's a good question.
Online.
The paper is online right now.
Okay.
The paper is online right now. We demonstrate some failure case and demonstrate some of the case without prompt tuning. But in general, if you don't tune your model, the model may not understand what's open the drawer. Let me put it this way. You may understand something apple, juice, cat, dog, was general concept of item, but doesn't necessarily understand the behavior, what's open the drawer, pick out things.
So only after the prompt tuning will be.
Exactly.
Very interesting thought. Thank you so much.
Well, thank you. Yeah.
I don't see any questions in the chat.
I think there might be a question.
If you have any, thank you guys.
If there are no questions, we can end here. Thank you again for speaking. This is great. And thank you folks for joining us remotely. I'm gonna end the seminar. Thank you.
Thank you.
Thank you.
Bye.